Well, hello from San Francisco. It's time to talk about estimation. Aren't you totally excited? I had to move my computer around. I'm so excited. Okay, this is going to be the first of a few videos. We're going to start with a few useful facts about estimation. Later on, we'll talk about what is a biased or unbiased estimator and get into some specific mathematical examples of estimating values with t-distributions and so forth. But let's just talk about this as kind of a high level view. Why estimate? Well, we could find the probability of one possible value, like is the mean 19.2? And we could look at the standard error of the mean and we could see how probable it is that the population mean is truly 19.2. And then we could ask, is it 11.2? And then we could ask again, is it 21.6? And we could keep on going like that forever. And obviously, it makes a lot more sense to find a range of plausible values than take every possible value that we could think of within a range and test that one and test that one and test the next one. So let's instead find a whole range of plausible values and say, we think that the range is somewhere, we got a value of 50. So we got a sample and we found that the mean for whatever this is 50. And that we think that means that the true mean of the population is somewhere between 30 and 70. It makes more sense to do it that way than try testing, is 31 a plausible value? It could be 32, right? So that kind of makes sense. Now, degrees of freedom, I'm not going to talk very much about it, but there's a section in your book about it. What do you mean by free to vary? Free of what? Well, if you know the mean of three numbers, say the mean is 5, and the first two numbers can be anything, but the third number has to be whatever that mean comes out to be 5. It's not free to vary. So if the first two numbers are 5 and 0, then the third number has to be 10. So the only way you can get a mean of 5 with three numbers, if the first two are 5 and 0, is if the third number is 10. It can't be anything else. If you're comparing two groups, each group has mean. For the first group, once you have all the numbers but one, that last number is determined. If the mean is 6 and the first two numbers are 10 and 4, the third number must be 4, right? Because 18 divided by 3 is 6. Can't be anything else. For the second group, the numbers are 4 and 10, and the mean is 5. Then the third number must be 1. That's the only way you can get a mean of 5. So for two groups, the mean is the number of records or people or whatever you have minus 2. Degrees of freedom doesn't really matter a whole lot, to be honest, for two reasons. One is unless you have a really small sample, if you have 9,998 people or 1,000 people that you're dividing a number by, it's not going to make a big difference, right? So unless you have a really small sample, it doesn't really matter. And honestly, these days, because it is 2026, any statistical software is going to compute your degrees of freedom automatically. But if you wonder what degrees of freedom are, now you know. The reasoning behind t-tests, first of all, let's say the standard error of the mean is the standard deviation divided by the square root of n, which it is. But that's the population standard deviation divided by the square root of n. But how many times do we really know the standard deviation for the whole population? Say for everyone in the United States. Not very often, right? So the reasoning is, since we don't really know what the standard deviation of the population is, and we're just making a guess at it based on the standard deviation we get from our sample, it stands to reason that we'll have a greater degree of error than if we weren't taking a guess at the standard deviation, because we don't really know what it is. We think because the standard deviation of the sample is 11, that it's 11 in the population, but we don't really know. And we're not just making a completely wild guess. And the more people we have in our sample, the more likely our estimated standard error is correct. If we have 1 million people, our chances of guessing the population standard error correctly are better than if we have 10 people. And you probably already have something like that in your brain, right? Like if I came to you and said, I did this study and I asked 10 people on Standing Rock, how important they thought politics were, and this is the value I got. And you would say, shut up, you only asked 10 people. But if I said I asked 3,000 people, you might be a little more convinced. The T distribution is a mathematical application of what you intuitively know. Even if you never took a statistics course, you probably figured if you don't sample very many people, you have more of a chance of getting the population value wrong than if you'd sampled a whole bunch of people. The fewer people in your sample, the wider the range of population values. That is, the wider our range of estimation is, because the fewer people, the more that you think you probably have some error. And a T distribution doesn't give you just one margin of error. The range of likely values gets bigger the smaller number of degrees of freedom you have. In other words, the smaller your sample is, the wider your margin of error, which kind of makes sense. And in the next couple of videos, we'll talk about a couple more things. One is biased estimators, because we're assuming right now things are unbiased. And we'll also talk about exactly how to find t-values and get a range of plausible values. But that's for videos in your future.